Now I'd like to introduce our next speaker, Carlos de Oliveira, from the President and CEO of CONNEX Corporation. Carlos.
So I hope you all have been very inspired to specify architecturally exposed structural steel and to incorporate steel into your architectural design for your buildings. And I'm going to take that to the next level. Lorena was talking a lot about steel in general, but whenever we're designing structural steel, we have to connect the steel elements together. And it's at these connection points that we can do really incredible things. We can express the flow of forces through the connections. We can create fluid structures. And in fact, through the use of steel castings, which is a different manufacturing approach, we can make really incredible structures that do incredible things. So our company exists to enable architects and engineers to use steel castings in their design. And we're really excited about it, as I said, because with steel castings, you can do incredible things from a structural perspective and also from an architectural perspective. And it's a real marriage between aesthetic design and structural design. And so we're very passionate about what we do, and we exist to help you leverage castings in your design. So what is a casting and why is it different from conventional structural steel? So what you see here is a hot rolling manufacture of an I-beam, or what we would call a W shape. A lot of people don't realize, though, that all steel is actually cast. So at the top of that image, you'll see actually that's a continuous casting process where molten metal is being poured continuously and is cooling and solidifying. And as it's still red hot, it's being rolled into the I shape that we're used to seeing. But with steel castings, what we do is we pour that molten metal into a complex shaped mold. And the steel actually freezes in that mold and takes the shape of that mold. And that's really exciting because we could make monolithic structural steel elements that have any shape imaginable. So what you're looking at here is a cast steel node. And this particular node is for use in an offshore wind turbine structure. As you're looking at that shape, appreciate that you couldn't possibly make that shape without castings. You can't roll and bend steel or weld it together to create that geometry. The only way to make that shape in a monolithic form is to pour molten metal into a mold and have it solidify in that mold. Now, when I look at that connection, I think it looks really sexy. And there's a lot of opportunity to leverage that kind of geometry and that sex appeal in structure to become part of the architectural language of buildings and spaces. Now, in actuality, though, this casting is being used in these wind turbine towers. It has nothing to do with aesthetics. The castings are actually enabling that structure to last 10 times longer in service because with casting materials, we can put the material where it ought to be for the flow of forces through those connections, and we can make highly optimized structural forms that can do things that conventional structural steel could never do. We move the welds away from regions of high stress concentration. We smooth out the flow of forces through those connections, and we can make highly robust structures that can withstand incredible loads, fatigue loads, earthquake loads, seismic loads, what have you. But of course, from an architectural perspective, the opportunities to leverage that manufacturing method can really open up design possibilities in architecturally exposed structural steel. So it didn't take long for architects to realize this and to start incorporating steel castings into their architecturally exposed structural steel. So here you see tree-like structures that are comprised of hollow structural steel sections and cast steel nodes. And those nodes at the intersection points where all of those structural members come together, they're obviously geometrically complex, they're highly loaded, they would be difficult to fabricate otherwise, but you can appreciate that that cast steel node is really selling the architecture or the design of that tree. That tree looks like a real tree because that's a casting. If that wasn't a casting, it'd be very difficult to cut those tubes together and have them come together and be able to carry those forces and look elegant, again, enabled with casting manufacturing. And as I said, with castings, we could put the material where it wants to be for the flow of forces through the connection, or we could kind of ignore it and we can just make really interesting looking connections. These particular connections are at the bottom of timber columns, obviously exposed at very close view, so people can actually go up and touch and feel these castings in the structure. And what I find particularly interesting is to see how people react to connection details like that in buildings. Having been in this space, you'll see children immediately just gravitate toward these connections, and they're touching them and they're trying to stick their head through it. And it's just interesting to see building occupants actually interacting with the structure. The structure is part of the feeling of the space. It really, with connection details, we can really make architecture sing. So when might castings make sense for your project? Well, there's a lot of opportunity to leverage castings, and the best uses are those that would tick off the most number on this list. Architecture exposed connections, obviously, particularly if the connections or the members framing into the connections are tubular sections, because those are typically difficult to connect anyway. And so with the castings, we can simplify those structural connections, but also express the connection. Complex connections where you have many members framing together, where the connection has to carry very arduous loading, high seismic applications, for example. Functional applications where we can leverage the geometric freedom of castings to address other constructional constraints. So for example, if we want to use a bolted connection to simplify construction, we can transition a structural member in an elegant way and maybe reduce construction costs. So there's an opportunity there to leverage castings. And finally, for fatigue critical connections, so if you're making a steel bridge structure, a pedestrian bridge, or a highway bridge structure, and it's going to be comprised of structural steel, there's definitely an opportunity there to leverage castings to not only improve the performance of that structure, increase its service life, but also to create very organic-looking connections. So nothing works better than to look at case studies of the use of castings to kind of understand what they can do for you as designers. This is a project in my hometown, which is Toronto, Canada. And in this structure, the Queen Richmond Centre Tower West, there was 2 existing heritage structures on a site that was surrounded with an L-shaped parking lot. And the developer decided that they wanted to build an 11-story office tower, but they wanted to actually put it up in the air above the existing 2 structures. And in so doing, they would create an L-shaped lobby underneath the new building that would be a public space. So it would, there would be retail in that space. It's publicly accessible. You can rent it out and get married in the space, for example. But basically, by putting this building up in the air, they're creating a public space inside. And you know, in Canada, it's pretty cold. So the fact that there's glazing and glass and you have this nice public space that's inside is also a benefit. And they decided to do it by using these very tall, 70-foot tall, architecturally exposed structural steel frames, on top of which they were going to perch this new building. The frames themselves were shaped for structural performance. They're part of the lateral system of the building above. So when the wind blows on that building above, those forces have to go through those frames, the lateral forces. And in addition, obviously, there's just a huge amount of gravity load going through those structural elements. So they're very much structure. But if you look at their shaping, they're also a form of art. When you go into that space, you forget that they're structured. They're part of the architectural aesthetic of that space. But you had a connection where you had 8 tubular elements framing together right in the middle, in the midsection of these frames, in something that was going to be exposed to view. Heavily loaded, complex geometry. Sounds like a good opportunity for castings. And so at first, when they were trying to address this, they looked at ways that you might fabricate that connection, introduce a big thick plate and splay the legs out. But you could see how a connection like that might not have been true to the original design intent, splaying out all the legs. And so one could use castings in a case like this. And in fact, that's what we did, is we developed a cast steel node that would work at the center point of that delta frame. Of course, being structural, it has to be designed for all of the forces that are being applied on that on the node. You can see how we shape the interior to reduce the stresses through that cast steel connection. Again, putting the material where it ought to be for those flow forces. But the exterior shaping is really driven by the aesthetic that the architect was after, to try and make it look like the legs were vertically continuous. That was the aesthetic that they wanted. They wanted basically 4 legs that looked vertically continuous. And you can kind of see that in this Revit model that now includes the cast node. And just to give you a sense of the scale of this connection, this particular casting was 32,000 pounds. The diameter on those legs is, I believe it was 40 inches and 2-inch wall thickness. Very, very big structure, but very important from an architectural perspective for this design. Here's the heat treatment of that casting. A step in the manufacturing process is to fully stress relieve the casting. Here you can see the finished product with machined nozzles where all of the structural steel is going to intersect. And here you can see as it's coming together in the field, at first with a temporary field bolted connection. And here you can appreciate the amount of force that's being applied through those connections. We're holding up an 11-story reinforced concrete office tower on top of those frames. And here you can see the finished structure. It's structure, but it's art. You walk into this space and you forget that these frames are actually holding a building above your head. Another project, perhaps on a lesser scale, but kind of a similar vein. This is at the University of Connecticut Innovation Partnership Building. Here, they were similarly wanted to support a structure up in the air. And in this case, it was going to be done on these V columns. And at first, when the designers were looking at this project, they had some ideas as to how they might articulate those connections. They were getting very complex and costly. They had to concrete fill the tubular legs of these V columns to address the forces. The connections themselves were getting very complicated and costly to fabricate. And at the end of the day, they didn't want to leave them exposed. So they were looking at potentially sheathing these structural connections. And as all of these costs started to kind of get worked out, they thought, well, why don't we think about castings? And sure enough, through the use of castings, we were able to eliminate the need to concrete fill those legs. We reduced the diameter of the tubular elements, and we incorporated the connections so that they could actually be exposed to view in the finished condition. So on the left here, you can see the V node that would be at the base of that V. And on the right, you can see actually what is a standardized casting, just one of the larger standardized castings that we offer, that would go at the top of that V. And here you can see that coming together in the field, again, painted in typical AESS white. Very simple, but it's part, obviously, of the expression of this space. And I would be remiss if I didn't talk about the Transbay Transit Center, which is, I believe, remains the single largest use of steel castings and architecturally exposed structural steel on the planet. 3.5 million pounds of steel castings, 304 castings ranging in weight from 6,000 pounds each to 45,000 pounds each. Wrapping the perimeter of the Transbay Transit Center, as you all well know, is a structural steel frame. But that frame is actually part of the seismic force resisting system of that building. So when an earthquake strikes, all of the lateral forces of that structure have to transmit down through these trees that wrap the perimeter. And you can see it's architecturally exposed steel. It's visible to view in the finished condition. But it's also, because it's part of the seismic force resisting system, it's very heavily loaded. And so the designers decided to use castings at all of the key critical junction points. And here you can get a sense of the scale of these particular castings. I'm not a particularly tall person, but I mean, that's still a big casting at the top there. And here you can see it, and you all watched it as it was coming together in your city. This particular junction point, which is what we call the Bostec level cast node, there's actually 7 structural elements all framing together. You have a tubular section coming in from the bottom. You have 2 drag struts coming in from the side and 2 from the rear. and then you have two tubular elements coming from the above. Again, all very heavily loaded, but with castings, we can make that transition look graceful. A section cut through the Transbay Transit Center shows its 150-foot tall light column or oculus structure. This particular structure is completely comprised of cast nodes and tubular connections. And this is particularly interesting because on the outside, those castings actually don't look that complex. You can see they're almost like just little macaroni noodles, if you will. But you can see the shaping on the inside where the casting is doing all of the work to address all of those forces. So that very simple, beautiful, elegant light column structure, the reason it's able to look like that, even though it's carrying so much force, is really because castings are doing all of the work on the inside. And so on the outside, it gets to look very simple and elegant. And here you can see that before it has been painted. And this is certainly going to be an excellent meeting space in your city. So everything I've been talking about up to this point has been related to custom designed castings, so castings that we would design specifically for your project and in collaboration with you. You know, you guys would be part of that process to determine the shaping, to express the structure in the way that you would like. But in addition to custom castings, there's a number of products out there that you can specify that are standardized off-the-shelf castings. So, you know, not everyone's designing the Transbay Transit Center every day, but certainly there's an opportunity to leverage standardized castings in any number of projects in any type. So here you can see one particular product. It's a universal pin connectors, and you can get a sense of scale and size that's available for these off-the-shelf components. And you can make true pin clevis type connections that can be left exposed to view, and for any number or any size of structural steel section that you might be able to specify. So a great example where these were used is the Whitney Museum of American Art in New York City, designed by Renzo Piano. Here you can see the X bracing that's visible at grade level. Interesting use of the connectors turned on their sides to make that X look almost as if it's floating in the air. And the same connectors that were specified here by Renzo Piano, they're a standardized off-the-shelf product. And here you can see them being used at the bases of these columns supporting a roof overhang in a library. So standardized castings offer the ability to leverage all of the benefits of castings, but without a lot of the cost because they're not custom designed. They're an off-the-shelf product. And they're very easy for fabricators to incorporate into their structural steel frame. So here, for example, you can see one of the pin connectors that's going to be welded onto the end of, say, a column or a brace. And that fabricator has mounted that member on a turning spindle, and that groove weld between the casting and the pipe is just going to be simply filled up with this automated welding machine. So it's very rapid fabrication of architecturally exposed structural steel that's very high quality and very low cost because they're standardized fittings. As I said, there's lots of different shapes and standardized castings that are available. There's tapered ends that you can use, say, for example, to pencil the top and bottoms of exposed columns. And you'd be surprised just by penciling just the tops and bottoms how it makes that whole column look more slender. You know, your structural engineer is saying, I need a certain size so that the column doesn't buckle. But at the ends, you can pencil it down and make that whole column look so much more slender. And there's standardized fittings that can allow you to do that. Or you can stack castings and mix and match them. So here you can see that those tapers are stacked with the pin connector, and they're used at these column base connections for these exposed columns. This is at Clark University, I believe. Similar use of those two castings stacked together to support, again, a roof overhang. This is a project in Boston. And a canopy column. Lots of opportunities to leverage castings to improve connection details. Here's those same two castings used together at the ends of timber elements. So, you know, you don't necessarily need to only use castings with structural steel. You could use them between precast concrete or cast-in-place concrete, timber, what have you. There's a lot of opportunity to leverage steel castings. And talking about timber connections, there's even castings that are specially designed only to mate to timber. So here, for example, are connectors that are designed to mate to the ends of timber columns or braces. And here you can see at the University of Massachusetts, those cast connections are used at the ends of timber elements in what they call the zipper truss. So this truss is supporting a roof that's actually accessible, but is obviously this truss is part of the architectural design of this space. And finally, as I mentioned, that there's a lot of opportunity to address structural complexity with castings. And so there's castings that have been designed to address specifically structural challenges. So here, for example, are castings that are for use in seismic resistant bracing. These are, because of the economy that they offer through the elimination of field welding, they're often used in industrial applications. So here you can see those connectors used at the ends of those braces that are supporting these very heavy tanks. This is in an industrial facility in California. But that same connector that was designed explicitly for functional purposes and seismic resistant connections often gets used in architecturally exposed steel as well. Just because when you're optimizing a structural connection, you often end up with something that looks elegant because nature is elegant, and if you put the material where it ought to be for the flow of forces, you're often left with something that looks rather elegant. So here is those same connectors used in those diagonal bracing in the Berkeley Art Museum and Pacific Film Archive. So just to summarize, architecturally exposed steel is a great opportunity for you guys to express structure in your architecture and make structure a part of your architectural design. And steel castings are an excellent opportunity for you to make expressive connection details and to express the flow of forces through connections to make economical structures and beautiful structures that we all have to live in for the rest of our lives, so they might as well be nice. So thank you very much for attending, and I hope you enjoy the rest of the evening. We're very proud to be sponsors, and thank you.